So hello and welcome students. I, Dr. Adil Patel, welcomes you for the discussion of the topic one compartment models. Now let us try to understand what is compartment modeling. So a physiologic system is often described by decomposition into a number of interactive subsystems called compartments. Now these compartments should not be understood as a physical volume but rather as a mass of well mixed homogeneous material that behaves uniformly. So you will not find any physical volume in the body which we are calling compartment, but instead it is a group of tissues and organs which are having similar behavior. So each compartment may exchange material with other compartments. Now let us see assumption of compartment models. So the body is represented as a series of compartments arranged in series or parallel to each other. So these are assumption, right? So in reality there is no clear cut system like the compartment models. For example, you cannot see a particular compartment in the body, but we have to assume that certain tissues and organs are behaving in such a manner that combinedly they are making a single compartment. The rate of drug movement between compartment is described by first order kinetic. So what is first order kinetic? The movement or the rate of drug movement depends on the concentration of drug. Now the rate constant are used to represent rate of entry into and exit from compartment. So the speed at which the drug is entering into a particular compartment and the speed at which it exits from that particular compartment. A statistical analysis of plasma concentration time data is another method used to find out number of compartments. So if you want to see how many compartments are there, then you can go for a statistical analysis of plasma concentration of drug. Now what are the applications of compartment modeling? So it is simple and flexible approach and widely used approach to understand the movement of drug inside the body. It gives a visual representation of various rate process involved in drug disposition. This concept is useful in predicting drug concentration time profile in both normal and pathological composition. It is useful in relating plasma drug levels in therapeutic and toxic levels. Now let us try to understand what is one compartment model. It is also known as the Instantaneous Distribution Model. So the time course of drug concentration determined after the administration can satisfactorily explained by assuming the body as a single well-mixed compartment with first order disposition process. So in the concept of one compartment, the entire body is assumed to be a single compartment. The body is constituted as a single kinetically homogeneous unit with no barriers to movement of drug. The elimination is a first order process with first order rate constant. That means the rate of elimination depends on the concentration of drug inside the body. The drug moves dynamically in and out of the compartment, then rate of input will be greater than the rate of output. So mostly what happens that the rate of administration is slightly higher than the rate of excretion. Now there is a slight modification in the concept of one compartment model, that is one compartment open model. So the term open indicates that the input, which is called the availability, and the output, that is the elimination, are unidirectional and that the drug can be eliminated from the body. So once the drug enters into the organs which are responsible for excretion, it will now go back to the plasma, and once the drug enters into the plasma, it will not go back to the original site of application. Now depending upon the rate of input, several one compartment models are defined. So one compartment open model, that is intravenous bolus administration. One compartment open model, that is continuous intravenous infusion. One compartment open model, extravascular zero order absorption, and one compartment open model, extravascular first order absorption. Now let us try to understand individual concepts. So intravenous bolus administration. So when a drug that distributes in body is given in the form of lipid intravenous injection, it takes about 1 or 3 minutes for complete circulation. The model can be diagrammatically depicted as you can see here, the blood and the other body tissues, and then there is a semi-permeable membrane kind of barriers which are available in the body, and from there the drug excrete out from the body. So Ke stands for the excretion constant for the drug. Now dx by dt is equal to rate in, that is the availability, minus the rate out, that is the elimination. Since the rate in or absorption is absent, the equation becomes dx by dt is equal to minus rate out. This is because we are directly putting drug into blood circulation. If the rate out or elimination follows first order kinetics, then the dx by dt is equal to minus Kex. So Ke is the first order elimination rate constant, and the x is the amount of drug in the body at any time remaining to be eliminated. This negative sign indicates that the drug is being lost from the body. Coming to the estimation of pharmacokinetic parameters. So for a drug that follows one compartment kinetics and administered as rapid intravenous injection, the decline in plasma drug concentration is only due to elimination of drug from the body and not due to distribution, the phase being called as elimination phase. Now this elimination phase can be characterized by three parameters: elimination rate constant, elimination half-life, and the clearance. In this figure you can see a graph of concentration versus time and the log concentration versus time, and as you can see that the increase in time is associated with corresponding decrease in concentration. So as the time increases, the concentration decreases. The straight line indicates a first order kinetic where the log concentration versus time gives you a straight line with negative slope. Now, what is elimination half-life? So it is defined as the time taken for the amount of drug in the body as well as plasma concentration to decline by one half or 50% of its initial value. So if you inject 100 milligram of drug in the body and you find that after 2 hours the concentration of drug is exactly 50%, that is the 50 milligram, then the half-life for that particular drug is 2 hours. Now in case of drugs where we do not know what is the half-life of drug, we can use this equation to find out the elimination half-life. So the equation is T half is equal to 0.693 divided by the first order rate constant for elimination, that is Ke. What is apparent volume of distribution? So these parameters are closely related with the physiologic mechanisms in the body. They are called as primary parameters. So the equation to calculate the apparent volume of distribution is Vd is equal to amount of drug in the body divided by plasma drug concentration. So capital X is the amount of the drug in the body and capital C is the plasma drug concentration. What is clearance? So clearance is defined as the theoretical volume of body fluid containing drug, the fraction of apparent volume of distribution for which the drug is completely removed in a given period of time. It is expressed in ml per minute or liters per hour. Now the total body clearance, that is CLT, also called as total systemic clearance. It is an additive property of individual organ or clearance. So the rate of clearance is equal to rate of elimination by kidney divided by the concentration of drug. Now let us discuss about the intravenous infusion. So a rapid intravenous injection is unsuitable when the drug has potential to precipitate toxicity or when maintenance of a stable concentration or amount of drug in the body is desired. In such a situation, the drug, for example, several antibiotics, theophylline, procainamide, etc., is administered at a constant rate, that is zero order by IV infusion. In contrast to the short duration of infusion of an IV bolus, that is for few seconds, the duration of constant rate infusion is usually much longer than the half-life of the drug. Now this particular graph would help you to understand the behavior of drug after intravenous infusion. So what happens in case of intravenous infusion, that after attaining the steady state concentration, the plasma drug level remains constant for the longer duration of time, and once you stop infusion, the drug will start getting cleared by various organs of the body. Next is the extravascular administration. So when a drug is administered by extravascular route, that is oral, intramuscular or rectal route, the absorption is prerequisite for its therapeutic activity. The rate of absorption may be described mathematically as a zero order or first order process. Now a large number of plasma concentration time profile can be described by a one compartment model with first order absorption and elimination. However, under certain conditions, the absorption of some drugs may be better described by assuming zero order, or you can say a constant rate kinetics. In this graph, you can see what is the regular plot and what is the semi-logarithmic plot of ARA, that is the amount remaining to be absorbed versus the time. So the distinction between the zero order and the first order absorption process is understood with the help of a graph ARA versus time. So ARA is the remaining drug to be absorbed, or the concentration of drug remaining to be absorbed versus time. So a straight line indicates zero order, whereas a curvature indicates first order. Opposite to that, when you plot log ARA, a straight line indicates first order and a curvature line indicates the zero order. Now this particular graph would help you to understand how the drug behaves when it follows the zero order absorption. So initially the drug concentration is 0, then with increase in drug administration and bioavailability, it goes to the highest level, that is the maximum concentration, whereas the rate of absorption becomes equal to the rate of elimination. And once the rate of absorption start decreasing, the rate of elimination start increasing. So in the later half, you can see that concentration is declining, right? So the Cmax is the maximum concentration and the Tmax is the time taken to reach the concentration maximum. So this graph is plasma drug concentration versus time graph, and at Cmax the absorption rate becomes equal to the elimination rate. So thank you very much students for joining. Let me know if you have any query or question. I would be happy to solve your questions and queries. So thank you very much again. Have a good day and stay safe.